Dear student, in today topic, we will discuss about the inner product spaces, and also we will study about the Graham-Schmidt process, which is generated by the inner product for getting the orthonormal basis. So first of all, the inner product. So the inner product is an important topic in this regard that as we all are familiar that how to make a product of two numbers. So what happens if we want to multiply two vectors? Or what happens when we multiply the two sequences or when we want to multiply two matrices? Is there any kind of product? So the answer is yes. So the inner product is actually the generalization of a product which are normally we are making the product of two real numbers, but this inner product is allow us to make a product of all kind of a vectors. For instance, instead of real numbers, we can now multiply the vectors, we can multiply the sequences, we can multiply the matrices, and this is actually the extension of the products. So basically, if we have two vectors from a vector space u and v, then this is the notion of inner product u comma v in that bracket. This type of signs is gives us a product when it satisfies the following conditions. Like the inner product of two vectors u v is always equal to the inner product of u v and u. Mean the inner product always satisfies the symmetric distance property, the symmetricness, and the inner product of u plus v with w is equal to the inner product of uw plus the inner product of vw. Mean it gives us this kind of a distribution under the additivity. The next thing is that the inner product of ku with v is equal to k times inner product with u and v. Means we can take the k common from that. Either you know it's a symmetric, so either it will be the k common in any of that vector where k is any scalar, so we can just take it common from that. And the inner product of two numbers is always two vectors is always greater than or equal to 0. Remember that inner product is a number, like either these are two, also these two are vectors. V is a vector, but v multiply with the v is gives us a real number, and that number is always greater than and equal to 0. Mean self inner product of two vector is greater than 0, and the inner product of the two vectors, two same vector is always equal to 0 if and only if v is equal to the 0. Mean that vector is equal to the 0. And if any real vector spaces that satisfies all these axioms, so it is called the real inner product space. And remember that these all properties are satisfied by real numbers. One can check that the product of two real number is also symmetric. It also satisfies these conditions, and it have this homogeneity axiom, and moreover it has a positivity. Like if you take the product of 4 and 5, so 4 and 5, 4 and 4 is always 16, which is greater than 0. The inner product of 0 with 0 is 0. Minus 1 and minus 1 is plus 1. So it always satisfies this thing. So now this is actually the extension of a product, and we call it inner product because it's take the inner product of all, not only the real numbers but also the all type of vectors or coming the elements they are coming from vector space. Like in Rn, we know that if we have two vectors u and v, then when we multiply the two vectors u and v, this is actually called the Euclidean inner product, and that is equal to the first element multiply with the first plus second element multiply with the second plus up to last element multiply with the last of that. So this type of a summation we will obtain, and remember that this will gives us a real number. So inner product is a real number. It can be 0, positive or negative, but remember that if the elements or vectors are same, then their product is greater than or equal to 0. And moreover, if the inner product is equal to 0, then this is happening only if when that vector is equal to the 0. So there are several examples of inner product which we will see later on, but that inner product also gives us a various kind of things. Like if we know that if we have the inner product of that one, the inner product with v and v, if we take its square root, then it will gives us a norm of v. Norms mean or the length of a vector we can obtain with the inner product. For instance, if we take inner product with v and v and then take its square root, it will give us the length of that vector from the origin. And also, if we want to compute the distance between two vectors u and v, that is equal to d of uv is equal to the norm of u minus v, and it is equal to the inner product of u minus v with u minus v and then its square root. And moreover, if the norm of any vector is 1, that is called a unit vector. Mean there are some vectors whose length is 1 from the origin, that vector we known as a unit vector. So there are some properties or some results regarding that one. Mean for instance, if u and v are two vectors from the real inner product space, real inner product space means v is a vector and we have a inner product on that. So note that the norm is always greater than 0 because norm is a non-negative real number, and norm is equal to 0 then if and only if the norm of that vector is the vector is itself 0. Mean if the vector is 0, then its length is also 0. And the k times norm of k v norm is equal to the absolute value of k times norm of v. The distance between u and v is always equal to the distance between v and u, and distance of uv is greater than equal to 0, and distance of uv is equal to 0 if u is equal to v. So it also satisfies the distance. Remember that from inner product we can induce a norm, and from also the inner product we can induce a distance d between the two vectors. This is also gives us a length between the two vectors. Then there is another interesting thing about the inner product. Like, can we make a weighted Euclidean inner product? The answer is yes. Euclidean inner product means the inner product of two vectors from Rn. For example, if we have a vector u and vector v from Rn, then we can define another form of its inner product, which is called weighted inner product. Like inner product of uv is equal to w1 u1 v1 plus w2 u2 v2 plus up to so on wn un vn, where these w1 w2 up to wn, these are some positive real numbers. Like if we have a positive numbers, then we can also assign another inner product which is called weighted inner product. For example, if you choose w1 equal to 2, w2 is equal to 3, w5 is equal to 6, like whatever that, and in this term it becomes the inner product because it fulfill all these conditions of a inner product. So this is called the weighted inner product. So this is the example of a weighted inner product. For instance, if u is a vector, u1 u2, v is a vector, uh, v1 v2 from the r square, and we can verify that this if we describe the inner product in this way, that inner product of u with v is equal to 3 times u1 v1 plus 2 times u2 v2, then it always satisfies the all above four axioms of the inner product space. Like these four axioms, it must be satisfied. And moreover, one can calculate. Look here, it shows that how it will satisfy these four axioms, and one can see these things over that. Like it fulfill all the criteria, and if the inner product of two number is equal to 0, then it's also then the vector is itself becomes 0. The inner product of self is equal to 0. Like inner product of v equal to 0, one can check that it is equal to 0, and if they are distinct, then if they are distinct, then their inner product is always greater than and equal to 0. Here these are the inner products defined by the others, like in the form of a like if we can express this type of inner product as well, where w1 w2 up to wn are positive real numbers. But remember that we cannot take them negative or is 0, because if we take a 0, then it will not become the inner product. I will show you one example regarding that. Here these are the some another examples. Like if u is a vector 1 comma 0, then we can compute its norm, which is the 1 square plus 0 square root, which is equal to 1. It means this gives us a unit length of a vector. So we can find the unit length in this way. And furthermore, we have if we change the weight Euclidean inner product, so this is the called the weighted Euclidean inner product, and look like we can compute these values in terms of that. So the length we can see that how to compute the norm of a u. Furthermore, the distance between u and v will be computed in this way. And remember that if the norm of any vector is equal to the 1, then it is called a unit vector. So we can also calculate this one. Now here these are some further examples of the unit circle. Like we can compute with that one with the help of inner product, and also from the ellipse we can see that weighted inner product give us this type of a structure geometrical shape of geometrical shape from this unit inner product. Now, this is another nice form of the inner product, that if we have any A is any invertible n cross n metric, square metric, then we can also define inner product U and V is equal to the AU dot AV. Mean whenever we multiply this metric with A with the first and the second with this, then still we can compute the inner product with the help of that. So this is the one of the good example of that one. So here you can also make the transpose of that. So this is called the weighted Euclidean inner product with the help of a matrices. For instance, like if we have some positive real number w1, w2 up to wn, then we can take a metric A with the help of that, and when we multiply this, then we can compute this kind of a inner product between the two vectors. For instance, here this is the weighted inner product. We like if u and v are the two vectors from from R2, then we can describe this inner product with this, like there is a metric A which has these entries, and you can check that if we apply this like in this way. For instance, here this one uh, like V transpose A transpose AU, if you compute the things like this, or in the above of that, because both are in the equivalent form, so it will always gives us a metric, the inner product between U and V. It means behind this inner product there is a standard metric. Okay, also here this is another example, like the trace of a two matrices will also gives us a inner product. For instance, if U and V are the two square matrices of n cross n, then the inner product between U and V is equal to the trace of U transpose and V. For instance, if U is this metric, V is a second metric, trace mean the sum of its diagonal entries. So first we need to multiply make the trace of that in some of its diagonal entries. So it will just like the give us a product of that entries, like u1, the u1 multiply with v1 plus u2 multiply with v2 plus u3 multiply with v3 plus u4 multiply with v4. So this is also satisfies all four axioms of a inner product space. Here, this is the example of that, like how one can compute the inner product with U and V, and how one can compute the norm of that. So remember that norm is always equal to the square root of inner product of U with U again. So now this is another good example about the standard linear product of a polynomial of degree n. For instance, if we have two polynomials of degree n, p and q, so we can multiply them. The inner product of p q is defined as a naught b naught plus a1 b1 plus up to a n bn. So this is called the inner product of the two polynomials. So it always satisfies the all four axiom, and in this way we can make the product of two polynomials, and one can check that. So these are the coefficients a naught, a1, an. Also the coefficients of q's are b naught, b1 up to bn. So if you multiply their coefficient respectively in the order form, then it will gives us the inner product between the two polynomials. And also the norm, you remember that norm is just the square root of a inner product with p, then it is becomes the a naught square plus a1 square up to a n square. And here there is an example of that one. One can check that this inner product satisfies the all four axioms of a inner product. So here we can see that this inner product fulfill all the axioms. And like here these are some computation of that one. For example, if we have a some x not equal to say minus 2, x1 is 0, x2 is the 2, and like let p not be the uh, evaluation inner product at that point. So then you need to compute the inner product with p and q and norm of p for the polynomials p is equal to x square, q equal to 1 plus x. So we know that how to make the inner product. The inner product is just like to making entries in the way like the inner product of PQ is equal to first we need to plug the values at minus 2, then we need to compute its value. It's just like we need to use this formula that the inner product is actually giving us the product of its values at their given points. So then we can compute these entries by simply put the values minus 2 over that and 0 and 2 on their respective places. And in this way, we can compute the inner product of P and Q and the norm of P. Now, with the help of this inner product, we can also make the product of two functions. The inner product of two function is always defined as if like f and g are the two continuous functions defined on the interval a to b, then inner product of f with g is equal to the integral from a to b f of x gx dx. So this is the standard formula. And remember that this equation number 12 satisfies all the four axioms of an inner product space. And we can compute, first of all, we can check that how it satisfies all the four axioms. One can check that the inner product of fg is equal to this, from where f and g we can interchange and it doesn't affect on its length or its area under the curve between f and g. And that is actually again equal to inner product with gf. It means inner product will always gives us a symmetric number. The inner product of f plus gh is, one can see that it is again equal to the inner product of fg plus inner product of gh, mean it satisfies this type of a distribution property. The inner product of k time fg is equal to the k times inner product with f and g. And moreover, the inner product of f with f is equal to the length between f square dx, which is always greater than or equal to 0. And moreover, if f is equal to the 0, then the integral from a to if the function is 0 at this, so one can see that the integral of a 0 function is equal to the 0. So it fulfill all the properties of that. Then the norm of a vector in space of all continuous function from a to b, like all continuous functions, one can see that the norm is actually equal to always equal to the inner product of f with f and then its square root. So in this way, one can see that the square root becomes in that form, and this is will be gives us the norm of a function. And moreover, if the norm is equal to 1, then we always call it unit function or unit like as a unit vector. So here there are some other like we have some other spaces which are the infinite dimensional spaces, and we can get the length of that one is the integral from a to b, the whole square root of f plus the f prime of x square dx, and then it's square root and then dx. So this will gives us the length of that one. So this is also the formula which normally we see in the calculus. Now here one can see that the norm always satisfies this type of of a useful properties that if there is any vector 0, then the inner product of 0 with v is equal to the 0, and it also satisfies this type of a distributive properties. So moreover, these are the useful, but here I can show you some results regarding that, which are actually the from the inner product. The first example you can see from here is that if we take uh, the inner product u with v is equal to u1 v1 only, where u is equal to the u1 u1 u2, v is equal to v1 v2, then this is not the inner product. Why? Because it will not fulfill the property of a inner product, that if we take the inner product of a two vectors, like if we have a vector u is equal to 0 1, then what happen? The inner product of a u if you take, then it will becomes only the inner product of a first entry, that because the product is defined in this way. So remember, it will always take 0 multiplied by 0, which is equal to 0. But the vector u is not a zero vector, because u is this vector, which is not a zero vector. It means it doesn't satisfy the property that the inner product of a self inner product of a vector is equal to 0 if and only if the vector is equal to 0. Here you can see that this is a very important property. The inner product of v with v is equal to 0 if and only if v is equal to 0. But here you have noticed that v is equal to 0. So it means if we this proves by the fourth axiom of a inner product. So it means this is not a inner product. In another example, you can see that if u is a vector 2 comma 0, v is a vector 0 comma 3, and then by using the Euclidean inner product from R square, which is the inner product of uv is u1 v1 plus u2 v2. So now what happen if we use this? We can compute the inner product with u and v is equal to this will becomes 0. And remember that if the inner product between any two vectors is equal to 0, then we call the both vectors are orthogonal to each other. Means here u is orthogonal to v and v is also orthogonal to u. We will see later on detail about the orthogonality. But here you can also check that what is the length of a u. Mean it will give us simply the square of 2 square plus 0 square root. Also the norm of v is equal to 0 square plus 3 square and square root, which is equal to the 3. And moreover, we can compute the distance between two vectors u and v with the help of this formula, that it is equal to the norm of u minus v, which is equal to the 2 minus 0 whole square plus 0 minus 3 whole square, and then its whole square root, which is equal to the square root of 13. Here there is also one interesting example, that the inner product defined on the set of all continuous functions, continuous real valued functions defined on the interval -1 to 1 is defined by the inner product of f and g in this way, where all f and g are coming from space of all continuous functions defined on from -1 to 1. So here one can see that the inner product with f f with f is equal to 0 for all f belongs to this one, means and moreover one can see that the inner product it have a this property that inner product is equal to 0 if and only if the the function is itself 0. Moreover, one can also check the property of additivity, that it fulfill this condition, that the inner product of f plus g with h is equal to the inner product of f with g and inner product f with h plus inner product of g with h. For all f and g are coming from the space of f, g, h are coming from the space of continuous functions defined from -1 to 1. And moreover it have a homogeneous property, so also one can check that it's also the have a symmetry of that one. So these are the one can see that the space if we define the inner product f with g in the way that it is integral from -1 to 1 f of x gx dx on the space of all continuous functions on the interval -1 to 1, then it is a inner product because it fulfill all the four axioms of inner product space. Now, the next thing is important about that one is so there are some properties and some of that one you can see that. Now, the angle in inner product spaces. So here we can see that the angle and the orthogonality in inner product space, like we can compute the angle between two vectors that is always equal to theta is equal to cos inverse of the u dot v is actually coming from the inner product. This dot product is actually the inner product between two vectors. So it means that if we have two vectors with the help of this, we can see the angle and the interesting thing is that this satisfies one inequality which is called the Cauchy-Schwarz inequality. This is very useful in the calculating some equations, and it is equal to it is the absolute of a inner product of u with v is always less than equal to the norm of u multiply with norm of v. So this is called the Cauchy-Schwarz inequality, and here then we have some of the examples regarding that. For example, if u is a vector in R4 and v is also a vector in R4, then we can find the angle between these two vectors. The angle between two vectors is actually the cos theta is equal to the inner product of u with v over norm of u with norm of v. So we know that how to compute the norms of u and v and also the inner product with u and v, then we can get the cos theta is equal to this value. And if we take theta, then cos inverse will becomes on the other side. So it means theta is equal to the cos inverse of -3 over 2 times square root 15. So in this way we can compute the angle between any two vectors. Here, these are also some properties of a norm that u plus this is called the triangular inequality, that the norm of u plus v is always less than the norm of u plus norm of v. Also, the distance satisfies the triangular inequality. The d of uv is always less than d of u with w plus d of v with w for any vectors u, v, and w coming from the some vector space. Now, the two vectors u and v are known as a orthogonal vector if their inner product is equal to 0. For example, if you have a two vector and if you multiply them, if their product is equal to 0, then the product, then you call it orthogonal vector. So this is the very important and interesting property. For instance, if you have a u vector is 1, 1, v is another vector 1, minus 1, and if we multiply u dot v, then it is equal to, it's a Euclidean inner product of r square, which is 1 multiplied with 1 plus 1 multiplied with minus 1. So if you make this calculation, the answer is 0. It means these two vectors are orthogonal. But if we use the weighted inner product with 3 and 2, here it can be any positive scalars, then one can check that this inner product is 1 under the weighted inner product, which is not equal to 0. It means under the weighted inner product, these are not orthogonal, but these are orthogonal in the Euclidean inner product space. Similarly, we can make the inner product if M is the inner product. We have in example number 6 from the previous section, and we have a two matrices, U and V are the matrices. Then these one can check that U and V, these two matrices are orthogonal to each other. How? Because if you take their inner product, like just take the trace of that one after its multiplication, the answer will becomes the 0. It means the inner product of that two matrices is 0. Hence, it means that these two matrices are orthogonal to each other. And furthermore, orthogonal vectors in P2, the space of all polynomials of degree 2. So if we take the inner product with x, with p is a polynomial x, q is a polynomial x square. One can compute the norm of p. So this is the norm of p. It's just like p times p means x times x is x square. And if you integrate x square first, so it will becomes x cubed by 3. And then put its upper limit minus lower limit in x cubed by 3, then it will becomes the 2 by 3 and the whole square root is on the top. Similarly, the norm of q is equal to, one can see that it's the square root of a 2 by 5 whole square root. And if we take the inner product with p and q, that is actually equal to the minus 1 to 1 x times x square dx, which is from integral from minus 1 to 1 x cubed by 3, that is equal to the 0. Like if you take them and it will becomes x cubed. So if you integrate, then it will becomes x4 by 4 and put upper limit minus lower limit. So it will becomes uh, 1 by 4 minus 1 by 4, that is equal to the 0. It means these two polynomials are orthogonal to each other. This orthogonality property is actually the very important in the linear algebra and analysis because it gives us a lot of important things. So, moreover, if the two vectors are orthogonal to each other, then the norm of u plus v is equal to square is equal to norm of u plus v whole square is equal to norm of u square plus norm of v square. So this is also the important property because if the vectors are orthogonal, then this inner product of u with v becomes 0. Here, this is some other examples of that one that it also satisfies this law we also called it's a Pythagoras law, which is always satisfies in that case. Now here this like if V is a subspace of inner product space, then the set of all vectors in V are orthogonal to the every vector W is called orthogonal complement of W, and it is denoted with the norm of it's denoted with the V this sign. So this is mean it's contain all the orthogonal vectors of that. So remember that the space of all orthogonal vectors is a subspace of V. Moreover, the vectors of the vector space W and its orthogonal contains only the zero vector, because zero vector is the only vector which is orthogonal to the all of the other vectors. So here there are some simple proofs of that one can see. And moreover, if you take orthogonal of any vector space, that is will again becomes a vector space W by itself. Here these are some examples of that, like if we, W1, W2, W3, W4, these are the these are the W1, W2, W3, W4 are the vectors in R6. Now find the basis of a orthogonal complement W. So here you can just take the vectors and apply the elementary operation on that on its columns. Then we can get the basis of that null spaces. And in this way, these W V1, V2, and V3 V1, V2, V3, these will becomes orthogonal vectors. Like if you multiply them, you will always see that these are orthogonal to each other. One of the interesting thing over that one is that how we can get orthogonal bases whenever we have some original bases are available. So orthogonal bases we can obtain by one method which is called the Gram-Schmidt process. Here we can see some examples of a Gram-Schmidt process, but first of all, we know that a set of two or more vectors in inner product is said to be the orthogonal if their inner product is equal to the 0. And moreover, remember that if we have a vectors and if we multiply them, they are orthogonal to each other, but they're like they are if their inner product is equal to 0 and the norm of that one, each of that vector is equal to 1, then these are called orthonormal vectors. For instance, here you can see if u1 is a vector 0 1 0, u2 is another vector 1 0 1, u3 is another vector 1 0 minus 1. Then one can see that if we make an inner product u1 with u2, then answer is 0. The inner product of u1 with u3, the answer is 0. The u2 with u3, the inner product is also equal to 0. It means these are orthogonal vectors. And these, since these are the bases of R3, so it means these are the orthogonal bases. And moreover, if we compute the norm of u1, the answer is 1. The norm of u2 is not 1. Norm of u3 is not equal to 1. But we can normalize it. Like if we have any vector, then for that vector, if we divide that vector with its norm, then in this way we can get a vector which is which is normal vector. Normal vector mean a vector whose length is equal to the one. Mean if v is any vector, then just multiply 1 over norm of v, then we will get a vector. That vector will becomes a unit vector, because if you take again the norm of that, the answer will be always equal to the 1. So it means that from any vector we can get a normal vector. Now here there is one interesting question arise, that if you have any vector, then can any basis, if you have some basis available, then can you find orthonormal basis? The answer is yes. But first we will see this example, like if we have a one if we have a vectors u1, u2 and u3 whose norms are available, then we can find the unit vector. Like v1 is a vector, just divide its norm with u1 over norm of u, then we will get this vector, which is already itself the same vector, and because the norm is 1. But this v, it will becomes a normal vector. u2, if we take v2 is equal to u2 divided by norm of u2, then again we will get a unit vector. u3 is the u3 norm of u3 is this, and if we divide the u3 by norm of u3, then we will get a vector v3. This v3 is a unit vector, because if you take again its norm, the answer will become the norm of v3 is 1. Now remember that v1, v2, v3, if you take inner product of them, the inner product of v1 with v2 is also equal to 0. The inner product of v2 with v3 is 0. The inner product of v1 and v3 is also 0. And moreover, the norm of v1 is equal to 1, norm of v2 is 1, norm of v3 is 1. It means their length is 1, as well as their inner product between each other is equal to 0. So it means v1, v2, v3 are orthonormal vectors. So orthonormal vectors are those vectors that inner product is equal to 0 and the length of that are equal to 1. Now one interesting question arises, that if we have any vectors, any basis or any basis of, suppose we have a basis of R3, can we get orthonormal basis from that given basis? The answer is yes. We have a one method, this is called the Gram-Schmidt process, and that Gram-Schmidt process allow us to get orthonormal basis. So look, if we have a one set S, V1, V2 up to Vn, these are orthogonal set of a non-zero vectors as a inner product space, then this set is S is linearly independent. So we can check that since these are orthonormal set, so the orthonormal set will always be linearly independent to each other. Here one can see that these E1, E2, En, these are orthonormal because the norm of E1 is 0. If you multiply E1 with E2, the inner product of E1 and E2 is equal to, the norm is 1, the norm of E1 is 1, and the inner product of E1 with E2 is 0. So similarly, if you take the inner product between that with any E1 and E2, the answer will be equal to the 0. So here one can see that we have some another example which shows these are orthonormal bases. Like we multiply v1 with v2, the inner product, multiply mean inner product. The answer is 0. V2 inner product with v3 is 0. v1 inner product with v3 is 0. And if we take the norm of v1, the answer is 1. The norm of v2 is 1. The norm of v3 is also 1. It means these are orthonormal vectors. v1, v2, v3s are orthonormal vectors or orthonormal bases of R3, because these are also the bases. Now, the Gram-Schmidt process allows us to obtain the orthonormal basis, and the method is quite simple. And here there are some proofs of that one, which I just omit due to the time base of that one. But it allow us to get the orthonormal basis of some of that. For instance, here one can check that we can get some orthonormal basis, but the question arises that if we have some basis of a any vector spaces, can we find the orthonormal basis? The answer is yes. So we have a formula which we can apply and get the orthonormal basis, and the formula is available over here, which we can see about that. And there is a method how to find the orthonormal basis. Like every non-zero finite dimensional inner product space has a orthonormal basis. Like if we have W1, sorry, U1, U2 up to UR will be the given basis of a some vector space W, then what we need to take is the first step, let V1 is equal to U1. Just take the first element as its same, and then find V2, which is equal to the U2 minus projection of U2 in terms of W1. It means it's the projection is actually the inner product of a U2 with V1 divided by norm of V1 square with V1. And if we compute this, we will get a V2. And this V2 is very interesting. This V2 will always perpendicular to the V1. And one can similarly take the V3 is equal to, by using again this, repeat this formula, where V3 is equal to the U3 minus inner product of a U2 V3, sorry, U3 with V1 divided by norm of V1 square with V1 minus the inner product of a U3 with V2 divided by norm of V2 square with V2. If we compute this, we will get V3. And interestingly, this V3 is orthogonal to V1 and V2. Means this the inner product of V1 with V2 is 0, the inner product of V1 with V3 is 0, the inner product of V2 and V3 is also 0. And in this way, we can combine all of that and we will get V1, V2, V3. These are orthogonal. Orthogonal mean only that inner product is equal to 0. But for but for getting the but for getting their normality, we just take the norm of that and divide the norm with each of that vector. And in this way, we will get some of that one, which are orthonormal. And here the Gram-Schmidt process step is available. Like if U1, U2, UR are available, then we can find V1, V2, V up to VR. These will gives us a orthogonal vectors, mean their inner product with each other is equal to 0, and we can normalize them by just dividing the norm with each of that. For instance, this is the example. Here we have a U1, U2, U3. These are the bases of a R3. Now, with just in the first step, as we know that find V1 is equal to U1, then compute U2, which is equal to V2 is equal to U2 minus this use this formula. This formula is very important, and this formula must be on your fingertip. This will this will remove the effect of that with the each other of that one, and it's make the perpendicularity or the orthogonality between these vectors. And when we apply this formula and after that computations, we will get V2, and similarly we get V3. And note that if you multiply V1 with V2, multiply V2 with V3, and also if you multiply V1 with V3, in all cases their inner product is equal to the 0. It means these all are orthogonal to each other. And when we get orthonormal, what we need to do is we just compute q1. In q1 we just divide the norm of that vectors over there. So if we divide the norm length of that one, then we will get q1, q2, q3, and these will becomes orthonormal. And one can check that the inner product of q1 with q2 is 0, the inner product of q1 with q3 is also 0, the inner product of q2 and q3 is also 0, and moreover the norm of q1 is 1, norm of q2 is 1, norm of q3 is 1. It means q1, q2 and q3 are orthonormal bases of R3. So conclusion is that from any given basis we can find orthonormal bases. Here the formula is also available for if we have a Legendre polynomials, so we can use this formula and we also can find orthonormal basis from the different cases. And in a finite dimensional vector spaces, every orthogonal set of a non-zero vectors can be enlarged to the orthonormal basis of a W. Mean any kind of basis we can convert to the orthonormal basis. Every orthonormal set in V can be enlarged to the orthonormal. So it means that for any kind of basis we have available, so we when we apply the orthonormal basis, we can interchange them into the form of orthonormal basis. And here there is one interesting decomposition with the help of that, like this is called the QR decomposition. If we have a Q and R are the two available matrices, like if A is any m cross n metric which have linearly independent column vectors, and Q is the matrix as a result of a Gram-Schmidt process. If we have a linearly independent vectors, then by Gram-Schmidt process we can apply that method, and it will becomes the orthonormal basis or orthogonal basis. So it will be given in a Q, and then the another metric R we can get. So it means between a metric A and Q there is a relation we can obtain with that, and that is called the QR decomposition. It means that if we have a metric A, then that metric we can write as a QR decomposition, where A is the metric taking the Q1, U1, U2 up to UN as a columns of that one. And if we apply the Gram-Schmidt process, we can get a Q, and there is another metric R. With the help of that, we can write its QR decomposition. And it means we can write A is equal to QR, where Q is a metric obtaining by the Gram-Schmidt process, and the other metric we can just obtain in the form of that, which is the upper triangular metric, obtaining these entries. So invertible upper triangular metric we can obtain by applying this inner product. So it will gives us the QR decomposition. Like if A is any m cross n metric with independent, linearly independent columns, then we can write A as A is equal to QR. And here you have noticed that if there is an example, A is a metric. If you apply the Gram-Schmidt process, we can find Q1, Q2, Q3 by U1, U2, and U3, where U1, U2, U3s are columns. And then we can also find R by given above formula, which will gives us a upper triangular metric. And note that if we multiply Q with R, the answer will be equal to A. The important thing is that A is any metric where the columns are independent. So this Q is the metric where all their vectors are these columns will be the orthogonal to each other. It's like it will gives us orthogonals, and the R is another upper triangular metric. So this is the useful property of that, like A can be transformed into this form. Here there are some another examples of that one, we have see the like how to use the Gram-Schmidt process to find the orthonormal basis. Here you can see that if we have these three vectors in R3, so take u1 is equal to the first one, U2 second, U3 is equal to third one. So apply the Gram-Schmidt process because Gram-Schmidt always convert the given basis to the orthonormal basis. First we find the V2, which is U2 minus inner product of these terms. So and then after using this, we by computation we will get the value of a V2. Now one can check that V2 is V2 is correct or not. Like if you take the inner product of V1 with V2, you can see that the answer will become 0. If the inner product of V1 and V2 is 0, it means V1 is orthogonal to V2 and the value is correct. Now again, if you need to compute V3, which is equal to the U3 minus these inner product terms by applying this is coming from the Gram-Schmidt process. So if you compute these values, after that, by employing there, you will get a vector V3. And one can check that the inner product of V1 with V3 is 0, the inner product of V2 with V3 is 0. It means V3 is the orthogonal to the V1 and V3. Now, after getting the values of V1, V2, V3, we can get the orthonormal that one. Normal mean whose that norm is equal to 1. So how we can compute this? Just take W1 as the vector V1 multiply with 1 over norm of V1. V2 as a is equal to V2. W2 is equal to V2 divided by the norm of V2. W3 is equal to V3 divided by the norm of V3. And in this way, we can get a vector V1, W1, W2, W3. And the W1, W2, W3 have a good thing that uh, the product of W1 and W2 is 0. The product of W1 and W3 is 0. The product of W2 and W3 is also 0. And moreover, if you compute their norms, the norms of all of that is equal to 1, means these are the orthonormal bases. So the Gram-Schmidt process allows us to obtain the orthonormal bases. Here there is another example. Like this example it will tell us that if T is a linear transformation from R3 to R3, because behind the matrices there is a linear transformation. So if we have a given basis set 1 0 0 1 2 1 1 2 2, then find the orthonormal basis. Use the usual inner product or Euclidean inner product with respect to the T, which is upper triangular metric. So here we need to apply the Gram-Schmidt process. Like take U1 is equal to the first, U2 second, U3 third, and then find V1 as equal to U1, then find V2, then find V3, and then after the computing its E1, E2, E3 by their dividing their norms, we will get E1, E2, E3. So these E1, E2, and E3s are the orthonormal vectors. These are also the orthonormal bases of R3. So in this way, we compute these things, the orthonormal bases. And now, after that, let's see some problems from the exercise, the assignments that we have. For instance, here, if in the first problem, U and V are the inner product on R2 generated by this metric, and let U is equal to 2, 1, V is available, W is available, then compute this inner product. So the inner product generated by that one, if this is available, then with the help of that, one can compute these inner products. So when you will see the topic that the inner product will be generated by any given matrix, we can compute their inner product. So this is the first problem. In the second problem, the inner product between the two polynomial of degree 2 is available in this way, then where P and Q's are available. When P and Q are available, then just need to find the inner product between P and Q. So P is a polynomial of degree 2, Q is a polynomial of degree 2. Just plug the values over there and one can compute the inner product between P and Q. In the next problem, number 27, we have the find the values of a k and l for which these all these vectors u and v and w which are mutually orthogonal to each other. We know that the vectors, when the vector will be orthogonal, then their inner product is equal to 0. What we need to do is that just make a product with u and v and u dot v, take u dot v equal to 0, take u dot w is equal to 0, take also v dot w is equal to 0, and this gives you the three equations, homogeneous equations. And when you solve it, you will get the values of L and K for which this makes it orthogonal. And in the problem number 28, T is a linear transformation with the standard matrix has the basis. So these are the bases of R3. Find the orthogonal basis of R3 by using the usual inner product. Here the method is same. You need to apply the Graham-Schmidt process as we saw in these practice examples, also some examples over here. Also the topic is available over here in the Graham-Schmidt process. These are the steps we need to apply, and then by using these steps we need to find the orthonormal basis. Like just take u1, u2 and u3, then need to find v1, v2, v3. Then after that you can compute the values of a e1, e2, e3 by making them normal vectors. Then these e1, e2 and e3 will becomes orthonormal basis of R3. So these are the questions of assignments. If you have any question, you can ask your question now.
Say, can I ask?
Yes, please.
On problem 26, do we replace px with p and qx with q, then find the integral of it?
In problem number 26,
Yes.
look, the P is available. This P should be the bold, like it's the P and Q you are available, you have available. So just put the P over here, Q over here, and then make them multiply. You know how to multiply these two equations, and then you need to integrate that from -1 to 1. If you integrate them, then it will gives you the inner product between P and Q.
Okay, thank you, sir.
Have you understand? I'm just saying put the value P over here. What is the P? P is equal to P of x. Here P mean P of x, which is 1 minus x square. So put 1 minus x plus x square over here, and Q is equal to 2 plus x square. You know, when you have the here two functions, you cannot multiply, you cannot get inner product unless you multiply them. First you need to multiply P with Q, and when you multiply you will get some polynomial of degree 4. Maybe it will becomes 2 plus, suppose 2 plus 3x plus 4x square plus 6x cube plus x power 4. Then take them integral, and you know the integral of it will becomes the integral of first, integral of 2 plus integral of the second term plus integral of third term plus up to so on. And then when you integrate them, and it will gives you one answer, and that answer will gives you the inner product of that. Okay, so here I think here there are some examples are available over here that how to compute the inner product of these. Look, like these are the polynomials. First you need to multiply. After multiplication you just need to break it in integral of first plus integral of second plus integral of third. Then uh, then make the integration of that all of this, and when you will after integration just making summation of that, you will get some answer, and that answer is actually equal to what? The integral of a integral of P and Q. In this way you need to compute. Any other question?
Okay, sir.
Sir, can you please explain problem number 27 again for me?
Okay. Look, do you know what is the orthogonal vector? The orthogonal vectors are those vectors when you multiply them, the answer is equal to 0. So here I just may tell you the summary that U is a vector, V is a vector, W is a vector. Find the values of K and L that makes the orthogonal to the vectors orthogonal to each other. Look, if you multiply V with W, is their product equal to 0? Here we can see that the answer may be not 0, but what the thing is, like if you just suppose that just take U multiply V is equal to 0, V multiplied by W is also 0, and make third equation that U multiplied by W is also 0. And when you solve all these three equations, then you will get the values of K and L, and when you put the values of K and L over there, you will see that the vectors becomes orthogonal. Like when you multiply U with V, the answer is 0. When you multiply U with W, the answer is again 0. When you multiply V with W, then answer will also 0. It means these are the all possible values of K and L that makes these vectors 0. That vectors are orthogonal to each other. So it means just take u dot the u dot v equal to 0, mean product of that is equal to 0, and vice all of that product, just u dot v 0, v dot w 0, and u dot w equal to 0. Then you will get three equations. After solving for the values of k and l, you will get the values of k and l for which these are orthogonal to each other.
Okay, thank you. I do understand now. Thank you so much.
Okay.
Say, can I ask
Yes, please.
on problem 25B or C or D, when taking those, do we turn a blind eye to that matrix that we're given there, the 0, -1, 2, or 1, or do we use it to solve that?
Sorry, which question you were asking?
25B or 25C or 25B, when we are answering those questions, do we use that matrix that we are given there, or do we turn a blind
Yes.
eye on it and focus on UVW?
No, look, the inner product is based on the look, U and V is an inner product which is generated by this metric. Okay, like it means the inner product is generated by this metric. It means this metric is also the part of that. And remember that here, if you will comes up and see that there is a rule that if there is an inner product generated with that, how to compute that. So it means A take inner product of UV means AU dot AV. So first A multiply with U, you will get first of that, and then A with V. So with the computation of that, this means that inner product is generated by A. So you need to apply this formula, and then you need to compute these inner products. And the sum of V is also equal to, the inner product of V with V, and then its square root. So the inner, instead of here in the A, uh, there is a metric available. This metric, this is your A in this case. You can suppose A is equal to matrix 0, -1, 2, and 1, as given in formula number 4. So again, I tell you that just need to multiply that metric with first vector, given metric with again with the second vector, and then make their product, UL product. Then it will gives you inner product generated by that given metric. It means that instead of just multiplication of that, you can also use some metric which also gives you the inner product generated by that given metric. Okay, if there is any other question, then you can ask. Uh, if there is no question, then we can close the session over here. So I hope you understand the problems, and when you will make a practice, then it will be make your concept more clear. Okay, best wishes and goodbye.